Thank you. As David said, I'm Mattia, and you will notice in my slides a lack of links, names, and logos. That's because I am no one and built nothing. I certainly don't have an endorsement from Ian LeCun, even though my wife said she's very proud of me. So there's that. I was just lurking on the Discord server when David was organizing this event, and I was also at the time studying, fiddling with some stuff that I find cool, and I hope you can find it cool as well. First things first, I'm going to talk about memory mapped I/O. Some questions. How many people here have embedded development experience? You. How many people have some experience with C code? Rust? Okay. Now, if you notice something wrong in my slides, that I say something that is not correct, please keep it to yourself. Don't try to steal my thunder, and you can politely tell me later. So, I/O stands for input and output, and it refers to anything that makes information go in and out of a processor. This typically involves stuff like keyboards or monitors, but today I want to focus on a different kind of processor. I'm going to use the Raspberry Pi Pico, which is an embedded board, as a background for my examples. I'm not going to delve into the details of the hardware, just keep it concrete by using some real-world examples. Those peripherals on an embedded platform are much more varied, something like lights, motors, sensors, any kind of communication ports. And those need to be physically wired inside your processor. And the code that runs on the processor needs some way to interact with them. Mapping those devices in memory is one way to do it, the most common and the most convenient, if you ask me. For example, on the Pi Pico, you have the first half a gigabyte of addresses in memory that is dedicated to actual SRAM. If you write and read in that, you're going to get results from RAM. Above that, there is a memory region dedicated to peripherals. There is something there that looks like memory, but isn't quite like it. Those are peripheral registers. There are words that, when written to, send a message to the device peripherals, and when read from, you get the state information about the device peripheral. It's like having a magical book where you can write a message, it gets delivered, and you get a response that you then have to interpret somewhat. Now, let's look at some examples. This is the datasheet for the Pi Pico, and this is one of the first registers you have to work with when you develop for the Pi Pico. It's the reset register, and it allows you to turn on every peripheral in the system. It is a 32-bit word, like every other register that we'll see today. It has a specific location in memory, and it is divided in many single bits. It has one bit for every peripheral in the system, and writing 0 to each bit turns on the peripheral. Now, what if we wanted to turn on the I/O bank 0, which is at bit number 5? Let's see how to do it in C. Since from the program's perspective, this looks like memory, we can just create a pointer to uint32, initialize it with the address of the register, which we have found in the datasheet, and I have conveniently placed it there. And one way to set bit number 5 to 0 is to simply write the memory pointed by the pointer to 0. This works, but it's a little bit rude, because you are also turning on every other peripheral in the system, every other bit in this register. We need a way to only set to 0 bit number 5. And we do that with bitwise operations. In C, those are represented by the ampersand and the pipe symbol and so on. Basically, what we need to do is to create an intermediate integer that has only bit number 5 set to 0 and every other bit set to 1. And then we apply a bitwise AND operator, and we get a register where every other bit has the same value as before, so we didn't disturb any other peripheral. And bit number 5 is finally set to 0. In C, this can be achieved by creating a word that has only bit number 5 set to 1 with the bit shift here, 1 shifted by 5 positions left. Then we reverse it with the little squiggly operator, and then we apply the bitwise end. This is simple enough, but most times registers don't have neat little bits stacked one on top of each other. They have fields that contain wider, they are wider, they have multiple bits. For example, this is a register that configures the system clock, and we have two fields, each of them 2 bits wide. What if we want to change the first field, source field, to a new value, let's say 2, without disturbing the other one? Well, we still use bit field operators. Just now we need a little more steps. We need to clear out the field bits number 0 and 1 by applying a bitwise AND operation, and then we need to OR in the new value, which is 2. Now, doing this by hand, as I've done before here with the assignment, would be quite troublesome. So it's best to define an abstraction for this task. In C, we do that with a simple function. The code is a little more convoluted, but it does exactly what I explained to you before. So we create the mask, we apply a bitwise AND operation to clear out the field, and then we apply a bitwise OR operation to write the final result. And then we use it by calling the function. This isn't exactly ideal because we have to call a function by passing 4 parameters: the register, the value, which are absolutely necessary, but then we have, in excess of that, the position of the field and the width of the field. It's a very simple task, and having to remember so many informations, it's a little too much for me, especially since I use raw integers instead of giving those a name. So let's give every valuable information a name and see if the situation improves. Not at first sight. I gave, with defines and enums, I gave a name to every possible value, every possible position and width. And the result, I mean, the informations are there. It's extremely clear if you read it all, but it's a lot more verbose. And names are a good source of documentation. We are taught that while programming, names are cheap, so we should also always give names to document what we're doing. The problem is, in a typical embedded platforms, there are thousands of registers, each register containing potentially multiple fields. If you have to give a name to every possible value, this cheap cost starts to pile up. It is especially important in C because it doesn't have namespacing support. So you have to introduce namespace by prefacing every name with all the information. And if you think I gave bad names to the values, those are taken verbatim from the datasheet. And it's very important that you keep the names in sync with the datasheet to understand what you're doing. So yeah, it's not exactly readable. We can somewhat improve the situation by using a feature of C, bit fields. Basically, we improve the representation of the peripheral register. Instead of using a simple uint32 pointer, we create a struct that mirrors closely the representation of the register through bit fields. We specify that the source field of the struct is 2 bits wide, and every other field and so on. Then we can create a pointer of the type struct instead of the type uint32, and accessing a single field is simply a matter of accessing the struct field. This is much more ergonomic, but has a couple of problems. First, it's not exactly guaranteed to work. Bit fields are a little fuzzy in C. There's a lot of undefined behavior. So it's not exactly portable, even though if you use the same compiler, you know it works, you can use it. It also loses control over the API you provide. For starters, we have to make sure that the pointer that accesses the registers are marked as volatile. Marking it volatile makes sure the compiler knows not to mangle with memory accesses. This is because during the optimization phase, the compiler may decide to change the order or the number of memory accesses. For example, if you write the same value to the same memory location twice, the compiler may decide to synthesize it in just one. But you can't do that because peripheral registers have side effect. Writing the same value twice is meaningful. So volatile tells the compiler, do not change the order or number of memory addresses that accesses that I'm using. And we need to make sure that the register is accessed with volatile accesses. And by using the struct, we are now, the data type is our API. The developer that defines the register may forget to add the volatile keyword. Then again, there are also a handful of registers in the system that have different access policies for fields inside the same word. For example, this is the tick register of the watchdog peripheral, and it has two fields that are read-only. Actually, that can be read and written. What happens if you write to a read-only field? I don't know. I have never done it, but the datasheet says to not do it, so let's not do it. Probably nothing. Okay, but it would be nice to engrave this constraint in the API. Now, at this point, I've shown you a few ways to do things, and I'm starting to see a pattern. You manually folding bits by assigning the value to the pointer is cumbersome, and we can't do it every time. So we define an abstraction. The abstraction works well, but it has a sterile interface. It has a lot of information, a lot of names. It's hard to read, hard to use. Being an abstraction, we could raise it, create another function that hides some more details of the implementation. But no abstraction is ever free. This may have an impact on performance, and even if it didn't, it still impacts you reading the code. It adds cognitive load. We can improve the situation by using a better representation instead of an abstraction, but this loses control. So we have a dichotomy between abstraction and representation. Unfortunately, C doesn't allow to mix and match well those two. You can't find a middle ground. You need to choose, pick your poison, basically. It's all good enough, really, but nothing perfect. Let's see if another language works better. Rust. High but also low-level programming language with a strong type system and modern features. How does it fare? Well, for starters, Rust has row pointers and volatile accesses as well. So everything that I've shown you in C can be done in Rust as well, just with a little more unsafe code to keep the compiler calm and steady. And you don't have volatile marked pointers. You have volatile access that are explicit with standard library functions. But other than that, everything works. However, you don't exactly work in Rust to use row pointers. We can do better, and we should. Let's see the namespace, the example of a function that writes to an arbitrary register implemented in Rust. Now, since Rust has so many good features, we can try to improve the situation. We can define a trait that associates the position and width of the field with the field value itself. So looking back at the clock configuration register, we define a trait that has associated a width and a position and a couple of methods helper methods to improve it. And then we define an enum that has the possible values for the field. We implement a trivial conversion to U32 for the enum, because apparently you have to. The enum, if you specify a value for the enum, you can use a cast in Rust. You can cast this enum to U32, and it will understand that you need the value, but it doesn't automatically implement into U32, which is very frustrating. Regardless, and then we can implement the trait for the enum, associating the position and width of the field with the value itself. Now, when we define a function that writes an arbitrary field in an arbitrary register, we only need to pass the field's value, assuming that it implements the trait. Then we can extract the data about position and width of the field from the trait itself, so we don't have as many parameters. This is an improvement over C. but it's still not ideal because yes, there are many registers in the system, and yes, they have many fields, all with potentially different values, but they also have the same values. You could have multiple fields that respond to the same enum. Then you would have to define a different enum for each of them, regardless, even if they are all the same, because you have to associate position and width, a different one for every enum. Also, we are trying to improve a C implementation in Rust. We can probably do better by just thinking in Rust in the first place. And what actual peripheral access libraries written in Rust do, usually, is to separate register access from register values, which is very clever. So let's do that. We create a structure that is generic over two type parameters, read and write. This structure simply wraps an address, and it has a read and write method that return type rectangle, which we will see in a moment, marked with the read parameter. Then the write method takes a read value struct marked with the write parameter, and then they ensure volatile access to the register. We also have a modify function that takes a closure, applies it to the register to modify parts of it. The write value struct, this is the register access. It handles writing and reading to the register. The register value is handled by another struct, which is generic over another type parameter, this spec. This struct simply wraps a word, a U32, which is the potential value for the register. It also implements a trigger conversion to U32. And it has a couple of helper methods to read a specific fields and write a specific field, not in the register itself, just in the wrapped word. This is for the library part. When we want to actually instantiate a register, we create even more types, empty types. That one of those. An empty type, which is the read specification that we use to specify that we want to implement the struct read value for the read specification, and we implement reading the 4 possible fields of the register. Then on the other hand, we implement read value again with the different type parameters. So we can say this is the right side of the register, and we have methods to write specific fields. Notice that we can read all 4 fields of the register, we can write only 2. Oh, sorry. Here I'm still using raw integers because this is all behind the API. This is the abstracted part. Now, and then you can simply use it by instantiating the register, passing the 2 specification type parameters, and the read method on the register access returns a read register value that you can expect with its methods, and the modify function passes you a write register access instance that you can use to modify the register. This register has different representation for read and write side, but if I just pass the same structure to both parameters there, I will get any register that can be read and written in its entirety. Now, all of this is extremely clever and sophisticated and completely unintelligible, at least for me. It is overly verbose and hard to navigate. You have to jump through hoops and loops to understand who does what. This is a struct that has type parameters that implements traits and so on. Keeping in mind that this is a very simplified version based on my understanding that could absolutely be flawed of what is usually done in a Rust peripheral access read. We cannot improve the situation through a better representation like we did in C, because unfortunately Rust doesn't allow for bit fields, which is a bummer, at least for me. And so, I mean, the usage is cool. The usage works really well. The problem is when you have to watch what's inside, then it becomes unreadable. And I would be pretty disappointed at this point, but I also have a big reveal. because the language that I think handles this best, given that this is a talk at an event called Zigtoberfest, is Zig. I'll leave you a moment to recover from the shock. Now, how does Zig fares? For starters, it can do basically anything that we have seen so far in terms of row pointers. It has volatile marker to ensure that read and write accesses are not mangled with. And it has, of course, pointers and so on. But Zig also has a precise representation of memory down to single bits. You can create a struct, specify exactly how big it should be, and for every field, specify exactly how big they should be. In terms of arbitrarily wide integer types. This is better than C's bit fields, not just because it is precisely defined, because you are using actual types. So if I say that the func field here is 5 bits wide, then when I try to write a value that requires more than 5 bits, I get a compiler error. That's great. In C, you get undefined behavior, which is the opposite of great. However, we can do even better because Zig allows to define similarly precise enum. I can declare an enum that is exactly 5 bits wide, associate a meaningful name to every possible value, and then when using it, I don't even need to specify the enum name, because the Z compiler is smart enough to recognize what type I'm talking about. So I can just say .co, which is very convenient when you are reading the datasheet. The datasheet says this is the value for CO, and the code just says that. You don't have to preface the func.co. Even better than that, Zig is deliciously anonymous. I don't need to give a specific name to the enum. I can just write it inline in the type specification. And again, this is extremely convenient because most likely the only time I'm ever going to use this enum is in the context of writing this specific field of this specific register. I don't need to give it a name. I can save on that cost. In terms of abstraction, in terms of representation, this is basically perfect, as good as it gets. But also, even representation has flaws, as we have seen. We would not now like to ensure that read and write accesses to the register are volatile, and also to maybe enforce specific policies for field access control. Now, the idea that I got from Rust to separate register access and values is good, so let's cling to it. Register values here are represented simply by those structs. The struct is the possible register value. On the other hand, register access is created in a similar way with a generic struct that takes as generic parameters the layout of the register, as we see before. It wraps a volatile pointer, so we know that every access to the register is volatile. And it implements read, write, and modify methods just like Rust does, except the read method already returns a cast to the layout struct. The write method takes an instance of the layout struct, and the modify method is a little different. Partly because Zig doesn't, you have, well, closures are less ergonomic in Zig, but also because we can do even better. The new value parameter here has its type erased. It's an any type, not a layout, because we want to modify one field at a time, not the whole register. And then it is assumed that when the developer calls this function, it will call it by using a struct, an anonymous struct, that is somewhat similar to the layout. It has more or less the same fields, just in a, not all of them. Then inside the modify function, we first read the value of the register, so we know what we're reading. Then we use a little bit of on-time magic to inspect the actual fields that have been passed to the function. And for each field, we replace the value that has been passed with the value that is contained in the register that is of type layout. so that we only replace the fields that we need. This is extremely enjoyable to work with. You just do the function, specify what fields you want to change and the value you want to keep. It's a little unfortunate that we have to erase the type of the parameter because types are a great formal documentation, but I can live with that. Now, what about proper access control? Read only, write only fields. We can do something like this. Declare an enum that specifies the access policy, and then associate an instance of this enum as a const declaration to the specific enum field. So for example, going back to the tick register, we had two registers, cycles and enable, which are read and write, and we have a running register that is read only. So we associate the field access with the enum, and we specify that yes, this is read only. Then the modify function becomes a little bit more complicated. We also inspect the fields in the layout type. For every field in the type that has been passed, we check if we have a correspondence in the original register. If we do, we check if it has an access field. If it does, we check what its value is, all at one time, of course. And if it's read-only, then we throw a compiler error, because you can try to modify a field that is read-only. Now, again, nothing happens if you write a read-only field, but you are probably making a mistake. You shouldn't do that, so the compiler tells you. And again, trying to set the tick register field running to not running will be caught as an error. Now, a little of wrapping up. We have seen C that works, but suffers a lot from namespace pollution, has only partial bit field support, and cannot really mix and match solutions. You have to settle for good enough, which is, of course, good enough. Rust is disappointing, really, because it has very modern features that mitigate all of the issues. No bit field support, I guess it's fine, but having no anonymous types, that's what really irks me. Because, again, you have a lot of ways to mitigate namespace pollution, but you are still suffering from it. The result of the API is good, it's very good, but when you have to read it, it becomes problematic. On the other hand, Zig has the richest set of features in terms of memory representation, but that's not really what's important here. What really wins the case is the structural type system and the ability to specify anonymous expressions in terms of types also. It's like it has the flexibility of a dynamic type system, also with comp time checking, which is the best. And the comp time code that is required to check invariants is complex, yes, but it's also very contained. It's only here. Those are 30 lines of code. Where is the complexity? Here, you can read it, you can understand it. Yes, the API is constantly changing as of now, so every time I go back into the issue, I need to slightly change my code because the standard library changed a bit, whatever. But it's also very straightforward code. It's not nothing fancy, it's just imperative code. Okay, with this I am done serenading Zig at a Zig event. There is just one more thing that someone may contest me with. All of this is typically done by metaprogramming. Rust peripheral access traits are all created with metaprogramming. Usually, the constructors of the processor provide information, documentation, and most importantly, XML documents that has a precise description of every peripheral. So you can write a program that reads this document and then prints out a peripheral access library. You don't have to do anything. The problem with this is that teaching machines how to code, it's a one-way trip towards the impending robot uprising, which is not ideal. Also, machine written code still needs to be human readable, because I am the human, I am the developer, I am working with it, and sometimes I have to unwrap it. And I have done this in both C and Rust for different reasons, and banged my head against libraries, machine-generated libraries, that are completely unreadable. So having the possibility of a program writing your own code is not an excuse to write lousy code. So we should still try to focus on improving this situation. And with this, I'm done with my rant. Thank you. Any questions?
Do you have any? Did you also check the effects on the binary size?
No.
Of the different implementations? Basically?
No, I haven't done that. That would be interesting, and I mean, there is certainly something to see. I can already tell you that the binary size for C will be the smallest. No questions asked. And I don't really know about Rust. There are a lot of promises of zero-cost abstractions, and I'm sure they're all precisely optimized, but I was focusing mostly on the human aspect of the thing. Probably Zig will have a sizable binary, because all that comp time code need to be reified at compile time. Zig need to implement a different function for every type parameter here. When I do this, every time I call this function, correct me if I'm wrong, Zig will have to create a different code that is especially tailored for the parameters that I pass. Now, Rust does this too, but this is there will be many more combinations if you use this API than in Rust. So yeah, I would say Zig would have the biggest binary. While writing code for these examples, I had to raise, I don't know exactly how it's called, the limit for comp time evaluation. Yeah, I had to set it from 1000 to 2000, I think, in my examples, which means that the compiler is evaluating a lot of code at compile time. So I would say that most likely C will be the smallest, probably followed by Rust, probably followed by Zig, but take me with a grain of salt there. Another thing that I glossed over, which is extremely interesting, is about undefined behavior. I've told you that bit fields in C are not exactly precise and portable. You aren't guaranteed that they will be in the order specified. This could be compiler dependent. They could be little endian or big endian. In Rust, you don't have that. You don't have bit fields, but you do have this. Here, I wrap the address of the register, and every time I want to read it, I convert it to a pointer and read the value. What is actually done usually in Rust peripheral access trait is they don't put an address, they put a word, and then they refer to the reference, which is still the address, but it's something different, to the reference of the struct, and they read and write using the reference. Now, I have it on good authority of a random blog post on the internet that this is actually not exactly correct. If you create a reference to a struct that is support, and then you say you can find this struct here in memory, here where the register is, you open yourself up to optimization bugs. Even if you use volatile access. Volatile access ensures that the compiler doesn't change the number, doesn't change the order of memory access, and doesn't remove your memory access. But the Rust compiler reserves the right to add memory access to references. If you create a reference and tell the Rust compiler, hey, you can find it here in memory, and it's a peripheral register, the compiler may, in some situations, decide to randomly read that memory. Because it's a reference, it's an object, it has a richer set of semantics, so it reserves the right to mess your code up. And technically, this is right. There is no fix for this. The fix is do not use references, which is extremely annoying. How much on a tight leash I have to keep the compiler not to mess my code up. Yes?
You should only have the ability to do that for the lifetime of the reference, though. So if you grab your pointer and then like turn the raw pointer into reference for some kind of limited scope, textual scope, then it should only be able to read it inside that scope.
I think that is correct.
Yeah, so
I'm not an
as
expert.
you make sure that you're allowed to read from that memory location inside the scope, then you shouldn't run into issues, but it's something you have to pay attention to.
Yeah, the point is that even read accessors to peripheral registers can have side effects. Even if you say, okay, I know that in this block the compiler may read randomly my peripheral register, but what if the peripheral is a communication port and reading to the from the register returns a byte that has been sent by someone? The compiler randomly reads it, you lose the byte.
Yeah.
So yeah, it's problematic. Sorry, there was.
You mentioned endiness in the C example. What happens with abstracts?
They guarantee nothing in this scenario. Packed struct, when you specify the struct as packed, you are.
No, I'm talking about Zig abstract.
Zig. Oh, sorry. Yes. By specifying it as packed, you ensure that Zig doesn't have padding between fields. So it is the struct is exactly mirrors the register. And yes, you have to specify packed in this case, otherwise there might be padding error.
Right. How does it behave in the case of like different endiness? Is my question.
I don't know.
I can tell you. The fact cell, like the first field, that's always the least significant bit. Going towards most significant. No matter the difference.
Okay. You also have a question?
Oh yeah, well, I wanted to comment on the size thing. Where you had the function call where you pass in an anonymous struct.
Yes.
Yeah, that one. So your point about that being basically a generic function that ends up having a bunch of different cognitive implementations, absolutely correct. But I would be surprised if you would not be able to match or surpass C in terms of size in this way. That function has a complete implementation, but at some point, I imagine that it lowers to explicitly one operation to set that address to a specific value. How you get there? Every step of the way that you get there, you make sure to mark as in line.
Yeah.
And that guarantees that you don't have overhead. Basically, that guarantees that boils down to, let's just say, with optimization on, but in a reliable way, that basically gets replaced with just the assignment at the end of the day.
Yeah.
So don't abuse inline. This would be a reasonable way of using inline. Don't use inline.
I didn't mark the methods as inline here because just for
maybe it's not even needed, by the way. But my point is, like, if you try it out, and it turns out that it's significantly bigger than both Zig than Rust and C in terms of executable size. Try adding in line.
Yeah.
That probably would make a change if that's the case.
Okay. Any more questions? Okay. Thank you.